Okay, so uh, we talked about thread pools. So two issues we were having. One, we were creating too many threads. When we create too many threads, the system is not going to allow us to do it. Right? The operating system has a max number of threads. You can't go over that. Now, what it can do is we talked about this. The first condition, we solved that problem. The race condition failed. We solved that problem entirely. Okay. But what about the other one? Well, I created a thread pool just so you can see what it looks like. I'm not asking you to recreate this. You can use mine as is. And just be aware there's some API things we need to talk about. Um, and I'm also going to talk about the perils of using AI to do homework and so forth. Um, it's kind of ugly. Um, but anyway, so we have some structs that we need to talk about. The first one, of course, is going to be our task. Our task has a function pointer and an argument pointer. Now, my function is not going to actually take any arguments because I'm just going to keep it simple. But that's identifies the task, right? Typical task pool. So what we're going to do is separate the thread from the actual task. And the only way to do that is create a task struct. Then we're going to create a thread pool definition, and it's going to have a queue. The queue is going to hold the jobs. As you might have guessed, it's going to hold the task. Then we're also going to have the thread IDs. So we need to be able to wait for them eventually. So we need to have those available for us. So we need those. And then we have a front, a rear, a count, and destroy. Okay. So front and rear, this is might not seem obvious to you, might not be at all, but this is definitely going to be a linked list. Do I have to create a linked list? No. Okay, excuse me, I said that wrong. It's not actually a linked list. We're just going to manage in a dynamic array of things. I'm sorry. My face hurts, so I'm doing the best I can. I'm sorry, guys. But anyway, your front and rears can identify which threads are which. Okay. The count identifies the total number of things tasked in the queue. Destroy is going to be a signal that we're going to be able to send our thread pool to indicate that there are no more tasks that are going to be created. In fact, we're waiting for threads to finish the work that is done. Now, this thread pool is going to be set up such that we're going to have a destroy method. That destroy method is going to actually go ahead and say, hey, no more things tasks are going to go in, clean out your queue, and finish. We're going to wait for all the threads. And so what that's going to happen is our threads, our worker queue, our worker threads are going to have to go realize, excuse me, that the thread pool needs to be destroyed and we need to clean up. Obviously, we need some mutexes. We only use the one mutex, so I can get rid of this now. But we're going to use two conditions. A condition is something we can signal to another thread, and we can have the thread wait. We can have a thread wait on a signal. And so we're going to have two conditions. One, which it's empty. When it's empty, that means there are no actual jobs in the queue. Thread pool is going to sit around and wait for jobs. When a job comes available, it's going to wake up and handle the job. So we have an empty. We have to signal when we're no longer empty. Because we have a max queue, right, of 30, we also want to have a full. So if the thread, sorry, my face hurts. So if our queue is full, we want to wait. We want to have the main thread wait. The user of um, the thread pool to wait until it's no longer full. We're also going to signal when it's full. All right. Sorry, guys. And both condition signals rely, or the conditional wait relies on a mutex. So the conditions are sent through the mutex, so it's important to remember that. All right. We have a thread pool, and for all sense and purposes, the pool that we're going to do is going to be that pool. Okay. So, okay. Sorry. Face hurts. So what we're going to do is, I'm going to get rid of this guy too, is we have init. We're going to go ahead and create our thread pool. So destroy is going to be set to 0. We don't want to destroy initially. We want that set to be off. Pool.front, pool.rear, and pool.count shall all be set to 0. Duh. Pretty simple. And then we're going to initialize our mutex. This is another way of doing that. And then we're going to initialize our two conditions. Nothing special to be done there. We're just going to initialize them. And then we're going to create however many threads we need to create. In I think in my case, I have 10. We're going to go ahead and create the 10 threads. And they're going to just sit there and wait. What method am I going to create with it? A worker thread. Note also that I'm storing the TIDs, the thread IDs. I am going to skip around a little bit so we can see what's happening. But when we go to destroy couldn't be simpler. We're going to set destroy to equal 1, and then we're going to wait for all the threads to finish. Okay. Note, it does not try to cancel, does not try to do anything special. It just simply dies off. Okay. We're going to go into worker thread in a second, but first I want to show you a task function. It just takes a number argument. It says the task is executing, blah, blah, blah. Nothing special there, just gives you a number. And as you can see, that number is going to be passed to it. When we add the task, we're going to pass the argument of the number to it. Pretty simple, nothing special there. So let's look at add task. So the first thing we're going to do, anytime we're going to modify pool, we're going to read pool variables, we're going to lock. So we want to lock the mutex. Then while pool count is equal to max Q, and we don't want to destroy, we're going to wait. Okay. Now, I probably did not need pool destroy here. And you go, why not? Well, the simple fact is, if we're adding a task, destroy should be set to 0, right? Should, no doubt. Yes, can't add a task after, and so forth. But as long as the max Q isn't met already, sorry, we're going to go ahead and create a task. So the thing we're going to take is our function and our argument. And we're going to set the pool queue. Then we're going to set the rear to the task. Then we're going to set the rear to be rear plus 1 mod max Q. It's going to increment. And pool count is plus plus. We're going to also signal that we're no longer empty. Okay? We don't quite know what that does yet, but we also want to note that we're going to signal here that we're no longer empty. And then we're going to unlock our mutex. Ta-da! Okay. Now we're ready for the magic. Okay? I want to show you one more time that while the max Q is met, we're going to go ahead and wait on a full condition using the mutex. Okay? It's very important that you use that same mutex. So you remember how some of your professor says forever loops are bad? Worker threads are another use of forever loops. So now we're going to lock our mutex. If pool count is 0 and we want to destroy, what are we going to do? We're going to unlock and break out of the while loop. Why? So we want to break out of the while loop, which ends the worker thread task. Okay? Pretty simple. So when somebody comes to join, it joins immediately, right? It's not doing something, it's joined. It's clean, it's ready to be cleaned up. Okay? While pool count is 0 and we don't want to destroy, we're going to go ahead and wait. What condition are we going to wait on? The empty condition. Okay? I have it printing wake up and so forth. If pool count does not equal 0, right, there are tasks to do, we want to do the task. So we're going to grab the front task. and we're going to move the front. Yes. And we're going to move the front. We're going to continually be moving these guys. This is not usually a great idea, but it actually allows it's um it's a queue implementation. It's a simple one, and it works. Okay. So and this is if you're wondering why we have that max Q here, it would wrap around once the end got too far over. It just simply wraps around. Okay, not really going to show you how the Q works. But pull count is negative, negative. We're going to decrement the pull count. As soon as we do that, we want to signal full. Anybody waiting for pull.full with the mutex is going to get notified. Then we unlock the pool task.function. Remember the function? We're going to go ahead and set it to task.arc. This is where the work actually gets done. This is where that function call actually occurs. This task function, that's where it actually occurs. And so forth. You'll note I have an else here. I just want to make sure that I'm unlocking in all situations. So somehow if I wake up here and there are no tasks to do for whatever reason, even though you're, wait a second, I woke up on empty, right? If pool count doesn't equal 0, right, we're going to do this. But if it does, that means somehow we woke up, another thread got the actual task, but there's nothing less for me to do. So we're going to clean up. Okay. I just unlock and goodbye. Okay. Pretty simple. Now, thread pool destroy makes a little bit more sense, but you'll note that I'm not actually locking the mutex here. I'm not. Why? Because nobody's ever trying to read it at the same time. It's being set once, not multiple times. We never have to deal with it. It's being checked, yes. Now this is designed, and you can actually see it run. I'm going to show you something else that you may be very unhappy about. But you can see that it runs all 49 tasks, even though it's got a max number of threads of 30. So it's just going to sit there and wait when it has to wait. Okay. Short running task, we typically do create a thread pool to do. And so that's, how we manage the situation in which you have two P threads. You have to actually do the work that you need to do and then have it wait to get action to be able to action. We don't typically do that with long running tasks. We do this with short running tasks. Pretty common. But there are times when this makes sense. When you don't know ahead of time how many things you're going to have to do, you may run this particular type of method. But most of the time, what we try to do is try to avoid situations where we're creating endless numbers of threads. That's usually considered a bad idea. Too many threads operating at once essentially destroys your ability to manage the CPU scheduling, essentially. CPU scheduling happens rapidly, but it has to happen so often that these waits and so forth make it next to impossible. So better to have fewer threads operate at any given time. Note that you can change this to 100, 300 pretty quickly, and it would still work. But we have to have a way of managing a pool, which is usually a group of threads, and then we have to give those threads tasks. The threads, when you have a pool, in C, we don't have simple data structures, unfortunately. And as a result, one thing I'm not doing here, and I really, really should be, is I'm not using a lot of free. I'm not freeing things when I'm done with them, but it clearly should be. Assuming a long running process. As a result, though, when we're doing this type of thing, we want to avoid long running things, number one. But more importantly, this is going to limit the number of total threads being created, and you can just simply add a task instead of starting the thread and as normal, you just add a task, as you can see. And then we can add that task and then it can go and it will do it when it can, when it gets a free thread to operate on. And so we do this for relatively short running things, but I'm going to just point something out real quick. I worked on this for about 2 hours. Um, and you're like, wait, what? Yeah. So I'm no stranger to AI. So I used AI tools. And trust me when I say that ChatGPT has yet to produce a working solution. None of this ever produced a working solution for me. No matter what I did or how many times I tried to make it work. Oops, I must have deleted something. Yes, I deleted something. I didn't mean to. Um, no matter how many times I tried to get it work, um, I'm not joking. The AI tools produced incorrect data. When I tried to use it for using it in the small, it actually made things worse on most occasions, um, continuously. And I'm not joking. Continuously made my life more difficult. So I just broke it out, cleaned it up, removed a lot of garbage. There were a lot more mutexes in the tool that you have. Um, I simplified the queue as well. A couple other things I did to make the AI tool work better. But ultimately, the AI tool, no matter how much I tried to prompt it, and keep in mind, I've been doing this for a long time. No matter how much I tried to prompt it, it kept making things worse instead of better. It was not working towards a completed solution. And in fact, I would tell it, hey, this isn't even going to compile. And it would give me more things that didn't compile. So just be aware. The AI tools are great. But if you're using them to speed your job up, great. If you're using them to do your work for you, that's usually very, very bad. And the reason for that is pretty simple. It's easier to work from a place where you have working code, and then you incrementally add things onto the working code. Why? Because immediately when you screw up, you know what you screwed up because you just did it. Um, So, and that makes problem solving a lot easier. I'm sorry, my face really hurts, so I'm going to end pretty quickly. But this is the second thing that we're trying to fix. Number one, we had the race condition failure, and then the too many threads failure is this other one. Thread pooling does handle that. Um, Threading is great. I would say thread pools, by the way, if you're trying to create even a simple one, this is a simple one, by the way. This does not do a lot of things it probably should be doing. There's no free in here. It's not freeing up memory at any point. Um, but anyway, my point is that even in a simple thread pool, this was locking and producing deadlock on a very, very regular basis, which is why it took me a long time to do it. If I think about how long it took me to do the actual work without AI, I probably spent about 30 minutes from a point of which I had working code and I made it work. One thing I'm also going to mention, this is going to seem odd when you're doing your homework or whatever you're doing. You'll note that a lot of the threading stuff we saw, okay, I'm actually going to go back here. Sorry. A lot of threading stuff we saw, oops. I just want one of these to work. I don't care which one. Right? We compile it without p threads and it runs. And you're like, how does it run? What is the deal with that? How is it working like that? And it's actually really simple. Okay. So for whatever reason, it can run some simple stuff, right? Simple threads. The caveat is when you get to the locks or the um, sorry, let me go back to the thread pool. We go down to conditional weights and the signals, it no longer works. So what we have to do in those cases, if we have to, we just have to do the p thread, and it does in fact work. I don't know why P1C is all of a sudden not working. It did work. It sure does. Yep. So when I tend to compile them myself, I tend to do it pretty quickly using the terminal. And the fact that if I press up, it actually gives me what I had before. But if you just add the pthread libraries in there, then all of a sudden, magically, the conditional signals and the weights and so forth work. And you're like, how does that work? Just as a reminder, I'm going to go over this one more time. Conditional weights are waiting on a signal. You identify which condition you're waiting on and a mutex. Okay. The signal that eventually you're going to have a conditional signal, right? The signal is going to have a mutex when you already do it. So you have the mutex, so you don't identify the mutex, you're just going to identify the signal. They just have to match. If you're conditionally waiting for something, when I conditionally signal, I have to have that same mutex. Otherwise, it's not going to work. Okay. But that's a waiting process. I'll make sure this code goes online. I appreciate, hopefully this wasn't too roundabout because my face hurts. But if you have any questions about it, please make sure you ask. I can go over this again in class next time you see each other, which will be next week, 11, I believe. But anyway, thank you guys. Have a great day.